Hello students, welcome to my YouTube channel Candid Chemistry.
In this video lecture, I will teach about isomerism of different organic compounds in detail. Let us discuss isomerism now. The concept of isomerism is an important feature of organic compounds. Two or more compounds having the same molecular formula but different structural formulas and properties are said to be isomers, and the phenomena is called isomerism. The structural formula of a compound shows the arrangement of atoms and bonds present in it. Isomerism is not only possible but common if the compound contains more than 3 carbon atoms. As the number of carbon atoms in a hydrocarbon increases, the number of possible isomers increases very rapidly. The 4-carbon compound butane has 3 isomers. When the number of carbon atom increases to 30, the number of isomerisms amount to over 4 billion. The following are examples of butane isomers which exist in the form of N-butane, which is a straight chain, or in the form of isobutane, which is a branched compound. Types of isomerism. The first type to be discussed is structural isomerism. The structural isomerism is not confined to hydrocarbons only. In fact, all classes of organic compounds and their derivatives show the phenomena of structural isomerism. The structural isomerism arises due to the difference in the arrangement of atoms within the molecule. The structural isomerism can be exhibited in 5 different ways. These are: Number 1, the chain isomerism. This type of isomerism arises due to the difference in the nature of carbon chain. For example, for pentane, which is C5H12, the following arrangements are possible. It can exist in the form of straight chain, which is N-pentane, or branch chain, which is isopentane or neopentane. Second type is position isomerism. This type of isomerism arises due to the difference in the position of same functional group on the carbon chain. The arrangement of carbon atoms remains the same. For example, if chlorine is being attached to the first carbon atom, it may be called 1-chloropropane, and if it is being attached to the second carbon of the chain, then it is being called 2-chloropropane. Third type is functional group isomerism. The compounds having the same molecular formula but different functional groups are said to exhibit functional group isomerism. For example, there are 2 compounds having the same molecular formula C2H6O but different arrangement of atoms, hence their functional group changes. One is supposed to be called as dimethyl ether while the other one is known as ethyl alcohol, although the number of carbon and hydrogen atom remains same. Fourth type is metamerism. This type of isomerism arises due to the unequal distribution of carbon atoms on either side of functional group. Such compounds belong to the same homologous series. For example, diethyl ether and diethyl N-propyl ether are metamers. For a ketonic compound having the molecular formula C5H10O, the following 2 metamers are possible: either diethyl ether or methyl N-propyl ether. Fifth type of structural isomerism is tautomerism. This type of isomerism arises due to shifting of proton from one atom to other in the same molecule. Let's see the examples below. One is supposed to be called as keto form, but with a shift in change of double bond as well as proton, it turns out to be enol form, where en means any alkene and ol is alcohol. Let us talk about the second type of isomerism in detail, which is known as cis-trans isomerism or geometrical isomerism. 2 carbon atoms joined by a single bond are capable of free rotation about it. However, when 2 carbon atoms are joined by a double bond, they cannot rotate freely. As a result, the relative possibilities of various groups attached to these carbon atoms get fixed and give rise to cis-trans isomers. Such compounds which possess the same structural formula but differ with respect to the position of identical groups in space are called cis-trans isomers, and the phenomena is known as cis-trans or geometric isomerism. The necessary and sufficient condition for a compound to exhibit geometric isomerism is that two groups attached to the same carbon must be different. Two butene can exist in the form of cis and trans isomers. If the two like groups are on the adjacent side or share the same side with one another, they are supposed to be called as cis isomer. If the like groups are on the very opposite side and cannot share the same side with one another, they are supposed to be called as trans isomers. The rotation of two carbon atoms joined by a double bond would happen only if the pi bond breaks. This ordinarily causes too much energy, making geometric isomers possible. The trans isomers are always more stable than the corresponding cis isomers. This is because in cis isomer, the bulky groups are on the same side of the double bond. The steric repulsion of groups makes the cis isomers less stable than the trans isomer, in which the bulky groups are far. They are on the opposite sides of the double bond. The geometric isomers have different physical and chemical properties. They can be separated by conventional physical techniques like fractional distillation, gas chromatography, etc. This slide shows the position of steric hindrance in trans isomer and cis isomers more clearly, and you can locate the position of like and different groups easily. Geometrical isomerism in cyclic compounds. Geometrical isomerism is also possible in cyclic compounds. There can be no rotation about carbon-carbon single bonds forming a ring, because rotation would break the bonds and break ring. For example, 1,2-dimethyl cyclopropane exists in two isomeric forms. In cis 1,2-dimethyl cyclopropane, the two methyl groups are on the same side of ring. In trans 1,2-dimethyl cyclopropane, they are on the opposite sides. A requirement for geometric isomerism in cyclic compounds is that there must be at least two other groups besides hydrogen on the ring, and these must be on different ring carbon atoms. Let us discuss the third type of isomerism, which is optical isomerism. In order to have a detailed discussion about this type of isomerism, let us clear some of the definitions. A plane of symmetry is supposed to be such a plane which divides an object into two symmetrical halves. A chiral molecule has a plane of symmetry. A symmetric object is referred to as achiral, whereas an object lacking a plane of symmetry is called disymmetric or chiral molecule. A chiral molecule has at least one asymmetric center and does not have a plane of symmetry. A carbon atom which is bonded to four different groups is called asymmetric carbon atom, as shown in the diagram below. It only means that a carbon atom is bonded to four different groups and that a molecule of this type lacks plane of symmetry. In order to understand optical isomerism even further, we need to have a clearer idea of optical activity. Light from ordinary electric lamp is composed of waves vibrating in many different planes. When it is passed through nickel prism, which is made out of calcite or calcium carbonate, or Polaroid lens, light is found to vibrate in only one plane, and it is supposed to be called as plane polarized or simply polarized light. The diagram below illustrates the vibration of ordinary and polarized light from a beam being propagated perpendicularly to the plane or paper. Solutions of some organic compounds have the ability to rotate the plane of polarized light. These compounds are said to be optically active. This property of an organic compound is called optical activity. The whole demonstration has been well explained in the diagram given. Optical activity in a compound is detected and measured by means of a polarimeter. When a solution of a known concentration of an optically active material is placed in the polarimeter, the beam of polarized light is rotated through a certain number of degrees, either to the right clockwise or to the left anticlockwise. It is indicated by the sign negative, whereas clockwise is indicated by the sign positive. The magnitude of rotation in degrees is referred to as observed rotation. Alpha shows the part of polarimeter. An optically active compound can exist in two isomeric forms, which rotate the plane of polarized light in opposite directions. These are called optical isomers, and the phenomena is known as optical isomerism. The isomer which rotates the plane of polarized light to the right or clockwise direction is called as dextrorotatory or plus isomer. The isomer which rotates the plane of polarized light to the left or anticlockwise direction is known as levorotatory isomer or negative sign. Let us discuss optical isomerism of lactic acid. Lactic acid, also known as 2-hydroxypropanoic acid, is an example of a compound which shows optical isomerism. It contains one asymmetric carbon atom as shown in the diagram. Two three-dimensional structures are possible for lactic acid. These structures are not identical because they cannot be superimposed on each other. On the mirror image of other such non-superimposable mirror images are optical isomers and are called enantiomers. Thus, three forms of lactic acids are known. Two are optically active and one is being optically inactive. One isomer is lactic acid positive, which rotates the plane of polarized light to the right or clockwise direction and is dextrorotatory in nature. The minus lactic acid rotates the plane of polarized light to the left or anticlockwise direction and is called levorotatory. Negative lactic acid is the mirror image of positive lactic acid and vice versa. The plus minus lactic acid, it does not rotate the plane of polarized light, that is, it is optically inactive. It is an equimolar mixture of plus and minus forms, which is supposed to be called as racemic mixture. The isomers have been well elaborated in the diagram below.
Students, I hope this video lecture was helpful to you. If you like this video, give it a thumbs up and don't forget to subscribe to my YouTube channel Candid Chemistry. Thank you.